Hello friends, this video will be a video about rotational motion. Although it's called rotational motion in your textbook in this chapter 8, it's really related to uniform circular motion. So I will call it non-uniform circular motion actually and cover it in here because it's quite strongly related. So this is again chapter 8 called rotational motion in your textbook. So if you want to go ahead and read about that in there, it's chapter 8 and I call it non-uniform circular motion because this really is non-uniform circular motion. What we learned is that we were rotating objects. They had an angular velocity, tangential velocity, centripetal acceleration, centripetal force. Everything is still there, but what is happening now, angular velocity and tangential velocities are not constant. So I'm going to redefine what we have in here in the context of non-constant angular and tangential velocities. So let's first define angular variables. And the first one will be angular displacement. This will be for a circular motion. Let me draw a circle in here. The object is rotating around the circle. Let's say this is a merry-go-round. You're sitting here rotating, and you have an angular velocity that is changing all the time. You're sitting in there, you're playing with your friends, and one of your friends, that's what generally happens in the playgrounds, rotates, keep rotating the merry-go-round faster and faster. So angular velocity will be changing. The distance, the angle actually you span in a certain time is called angular displacement. So again, the angular displacement is the angle span in a certain time. So if the time passes t, and theta is the angle spanned, and this distance you traveled along the circle is s, generally called s. This distance you traveled along the circle is actually arc length you traveled. Theta can be defined as s over t, and its unit will be radian. Here we will be using, for angles we will be using radian, and it's equal to arc length traveled over time. So this is angular displacement, angle spanned in a certain amount of time. Since we'll be talking about more radians in here, I want to review our information for radian in degrees. We will be, if we are given the angular displacement in degrees, we're going to be converting into radian. Generally it's given in radian. We won't be really quite often doing that, but I want to define to you what radian and degree is, how they're converted to help you understand this fact better. So let me put here radian and degree angles. If we have a full circle, I am sure all of you know in degrees what every position along a circle means. We know from the general information of life that if we rotate a full circle, the total angle you rotated is at 360 degrees. Let's say we start from here. This is our initial position. This is 0 degree point. If you come in here, this is 90 degree. We can see this 90 degree from here, remember it. And if you rotate one half circle, you're here, you rotated 180 degrees, so this whole degree is 180. Continue rotating, here you have 270 degrees. And coming back to 0 position, you will have 360 degrees. 0 and 360 degrees are the same position, except you now rotated a full circle. Its full angle is 360 degrees. Radian is only another way of expressing these degrees. It doesn't actually have a unit as radian. We call it radian, but it is a number only. That's why we were just taking out of the blue. We were having omega frequency, angular velocity as radian per second. But radian is not actually a different unit. It's a number. How is radian defined is that if we have a circle with radius r, and we travel along the circle, we go to the distance along the circle that has an arc equal to r. The angle we span is 1 radian. That's how it is described. But how we more often see this in life is that we start from 0 radian as well, very similar to degree. When we come up in here to 90 degree, we have pi over 2. When we rotate a half circle, come in here, we travel pi radian. Come in here, we have 3 pi over 2. Coming back to 0 position, we have 2 pi. This is generally known way of expressing degree in radian. We express the radian in terms of pi. And what is pi is actually a constant number. There's a very interesting story about that. Actually, I'll put it in here and delete it. You don't really have to know that. Pi is about 3.14, constant number. And it's discovered when the mathematicians in the beginning studied circles, and they said they found that whatever the radius is, doesn't matter. If you find the circumference of a circle, let me call this circumference, circ as circumference, and divided by the diameter of the circle, which is equal to 2r. So circumference divided by diameter is always equal to the same number, 3.4444 actually, 3.14 or 133 continually approximately 3.14. It's always equal to 3.14. And then this was accepted to be a constant, like a universal gravitational constant, as pi. And we start to express the angles in terms of pi. So pi is always equal to circumference of a circle divided by the diameter of it, which is equal to 2r. And which is why we are always calculating circumference of any circle to be equal to 2 pi r. This is extra information. If you want to go and watch a nice YouTube video, just search online how is the pi discovered and so on. There are very nice videos explaining that. But pi is actually a number, and we generally express radian in terms of pi's, but what 1 radian is, when we travel along the circle, an arc distance that is equal to r, we have 1 radian. And what they are corresponding in terms of angles is 0 radian, pi over 2 is 90, pi is 180, 3 pi over 2 is 270, and 2 pi is equal to 360. In converting from radian to degree, I'm going to delete this now. If we needed any question, if the angular displacement is given in degrees, you have to convert into radian. So converting radian to degree, let's say we have pi radian, or whatever we have, because it's in radian, we multiply this by 180 degree divided by pi. So radian times 180 divided by pi converts the radian to degree. From degree to radian, we do the opposite. We do the opposite. We take degree angle multiplied by pi over 180. Degrees will cancel, and we'll be left with pi. We'll be explaining the angles in terms of pi. Pi radian is the same thing. Again, pi is only a number. So this is extra information. Learning from degree to radian, radian to degree. Only in some questions, angular displacement could be given in degree, and you might need to convert to radian. We won't be really needing it, but it's an important information to know in case we will need it in the future. So this is angular displacement expressed as S over R, and its unit is radian. And shortly we will show it as rad. We also have angular velocity here, the same angular velocity as the uniform circular motion, except now this angular velocity is not constant, it is changing. So the angular velocity, omega, this is actually a Greek letter, slightly different than W, but you can also call it W, it doesn't really matter. Omega is the angle span per unit time. We defined it that already in uniform circular motion. It is the same thing here, angle span per unit time. We're spanning an angle in a unit time, and our angular velocity is omega. And it is equal to, we'll be looking at average angular velocity now because it is changing now. So we'll call average angular velocity is equal to change of the angle delta theta divided by change of time. Again, like in the beginning when we are defining velocity, average acceleration will be the same. We'll be dropping the average sign. We'll be just calling this omega, but what we will be looking at is average angular velocity. Now, if the angular velocity is changing, that means there is a change of angular velocity per unit time. And change of velocity per unit time generally produces an acceleration, what we will call angular acceleration. Let me put it in here so we can see all these three definitions in the same place. So 3, we will have an angular acceleration. This is the change of angular velocity per unit time. We will call this alpha, new type of acceleration, and alpha will be equal to, we'll take an average alpha, we'll drop the average sign later on, will be equal to delta omega, change of angular velocity in unit time, delta t. The unit for angular acceleration will be rad per second squared, similar to meters per second squared in regular acceleration. And unit for angular velocity we already knew will be rad per second. And any given angle again should be in radian to solve for angular velocity, from where we can solve for alpha, angular acceleration. These are the angular variables in this motion. So we have rotation and angular variables. Now, I'm going to jump into showing you the directions of these angular velocity and angular acceleration. I'm going to delete this. This is an extra information that we're going to use in the future when we come to cover torques and angular momentum. So directions of angular variables. Let's say we have a disk rotating in this direction. What I showed so far in terms of angular velocity was actually showing the direction of motion. So this is the direction of motion. To find the direction of angular velocity, the actual vector direction of angular velocity, we wrap our hand around the direction of motion, holding the object that is rotating, and the point that our thumb is directed is the direction that our thumb is pointing is the direction of angular velocity. So if this disc was rotating on the horizontal in here, I'm holding it and my thumb is showing up direction. This will be the direction of angular velocity, omega. This is how it is really working in real life. If the direction of motion was opposite, so now this disc is along horizontal again, rotating in this direction, then we again hold it, wrap it with our four fingers, and the direction of our thumb is again the direction of angular velocity. So it's down in here. This is the direction of angular velocity. For angular acceleration, similar to velocity, we said acceleration is the same direction of velocity. If an object is acceleration, opposite in the direction of, to the direction of velocity if an object is decelerating. Same goes in here. Acceleration alpha, angular acceleration alpha will be in the same direction if the object is accelerating, rotating, and each certain time, unit time, omega is increasing. So object is accelerating, let's say in here. Acceleration in the same direction of the velocity, angular acceleration, angular velocity, only the change in here. Same goes in here. Alpha will be in the same direction of omega, object is accelerating. If the object is decelerating, let me draw them in here as well. Let's say we have the same directional rotation. We'll wrap our hands, this was the opposite, sorry. Wrap our hands, direction of angular velocity, upward here. Wrap our hand, direction of angular velocity, downward. And the object is decelerating now. Then the direction of angular acceleration will be in opposite direction. Here we will have alpha downward. Here we will have alpha upward. Let me draw it this way. Because object is decelerating, acceleration is in the opposite direction to velocity, same as in kinematics. Now, how do we solve questions here? Actually, it's very simple. Very same as the kinematics solution. We had 1D kinematics, 2D kinematics, and equations. What we're going to do is to change the variables in these equations, apply them to rotational motion, and we are done. We already know what to do there, and let me show you those. So this is the direction. Deleting this now. This one we're going to reuse again in the torque section. This actually provides an angular momentum in the direction, perpendicular direction of rotation, and it causes equilibrium of the objects. Actually, it helps you to draw your bicycle. If you rotate your bicycle and go, you maintain balance. And if you let it stop, it falls down. This is the reason. When you rotate it, you have this angular acceleration. It gives it a force to keep it alive, to keep it up. It's very interesting. We'll get there later on. But let me now give you the equations for all these rotational motion. So the title I'm going to put here, actually what I prefer to call this is rotational kinematics. I put rotational motion because it's the title in your book, kinematics. It's exactly the kinematics of rotations. Change in velocities, and we'll be looking at times and displacement in the angular version, angular respect. So, equations for rotational kinematics. The equations we learned so far, 1D, 2D kinematics, were linear along a line or into 2 dimensions. We generally had straight lines going in 1 and 2 dimensions. Now we have circles going around. That's the only difference. So we will be taking the equations from kinematics. Let me write down kinematics equation. I'll put here linear. These are the ones we already know. If we have a constant speed, we have x is equal to v times t. There's no acceleration. A is 0. If we have varying speed, and v is constant. If we have varying speed, we had v final is equal to v initial plus at, one equation concerning initial final velocities, acceleration, and time. I hope you remember those. We also had an equation relating final velocity, initial velocity, acceleration, and the distance, displacement, helping us solving different types of questions. And the general equation we had for displacement was v0, initial velocity times time, plus 1 over 2 at squared. And this case was for the accelerating case, right? Again, if an object is accelerating, velocity and acceleration are in the same direction. And we have plus here for every term involving acceleration. And what did we do to remember? Simply what we do if we have a deceleration was that. Let me put this on that side. You can see that right there. For the deceleration, decelerating objects, we have exactly the same equations. This is the same because acceleration is 0 anyway. These will be having minuses instead of pluses. So let me also remind you that we will have V final. We call V final V is equal to V0 minus AT. So this corresponds to that. We have V final squared is equal to V0 squared minus 2AX, corresponding to that motion, decelerating case, and we have X is equal to V0T1 minus 1 over 2AT squared, displacement. So values, acceleration, values, deceleration. Now let's move on to values or equations, to be a better word, for rotational kinetics. Now we move on to rotational kinetics. Let me put this kinematic equations for rotation. We will be replacing x by theta. Okay, replace. Because instead of displacement along a line, we have displacement along an angle, right? Spanned angle. We will be replacing velocity by omega. Instead of a linear velocity, now we have a circular velocity, what we call angular velocity. And we will be replacing acceleration A by alpha. Everything else will be the same. So let's do that actually. Let's write down accelerating case. We will have theta is equal to V omega t if acceleration alpha is 0, right? We will have this final omega, final angular velocity, replacing, is equal to initial angular velocity plus alpha times t, time is the same. We have final angular velocity squared is equal to initial angular velocity squared plus 2 alpha theta. So A is for alpha, X is for theta. Angular acceleration, angular displacement. And instead of X, I have theta is equal to omega 0 times plus 1 over 2 alpha times squared. These are for acceleration. Again, all I did, this is only separate acceleration is 0. All I did was to replace X by theta, V by omega, and A by alpha. Okay, for deceleration, you know what to do. We are now pretty experienced on that, right? We're experts. In terms of in front of any term involving alpha, which is corresponding to A in here, instead of plus, we'll put minus, and the equations will be the same. So let's do that. For decelerating, we will have final omega, angular velocity is equal to initial omega minus alpha times t. We will have final omega squared is equal to initial omega squared minus 2 alpha times theta, displacement. And we will have for theta, angular displacement, initial omega times time minus 1 over 2 alpha times squared. And these will be applicable to decelerating cases. Whenever we are asked a question, there will be displacement in terms of theta, there will be velocity in terms of angular velocity, acceleration in terms of angular acceleration, except for that, we're all the same as in kinematics. Instead of going a straight line or two-dimension, up and down, right and left, we will be rotating and looking at a position, a point in a rotating object to see how much it is moved along the circle, how much angle it spanned, what is its circular velocity, which is called angular velocity, what is the angular span, which is called theta, angular displacement, what is the angular acceleration, which is defining how much its angular velocity is changing per unit time. Let's now solve some problems to understand this better. I am going to delete these, and I'm going to remind you what equation we will make for each question. I believe I have 2 questions to solve for you. I'm not going to put a pre-lecture quiz for this one. We're going to start solving questions tomorrow in class, and I'm going to talk to you about pre-lectures in the class tomorrow. So let me find my question, my example. Let me try to draw this thing. It's a blender we have, a real life situation. So we have a blender here. Oh, my blender is terrible. So it is connected to an outlet in here. And it's working. And when blender is working, we know it's rotating. Around the center, it has an angular velocity actually. It will have an alpha angular velocity. And we can push different buttons in here to change this. Angular velocity and acceleration will be there then, because the angular velocity will be increasing or decreasing. So this question is covered in that, and let me read it to you. The blades of an electric blender are whirling with an angular velocity of 374 radian per second. So let me take this away. Initially, right, what the blades have as an angular velocity is 374 radian per second, rad per sec. So they are rotating with this angular velocity. And let's see what will happen next. When the puree button is pushed, so we push a puree button, the blades accelerate and reach a greater angular velocity after the blades have rotated an angular displacement of 44 rad. So we push the puree button in here, accelerate the blades, and it starts rotating faster and faster. This angular velocity starts increasing. So the blades will have an angular accelerations, we don't know, but it says until it reaches a certain velocity later on, it has an angular displacement of 44 radian. If you see plus and minus in this angular displacement, general convention is to use clockwise positive, counterclockwise negative. We won't be really sticking with that. We won't be really dealing with these directions too much, but that is a good thing to know. In this question, we have this is plus, so this turn clockwise rotation direction. Just so you won't be confused when you see plus and minus in a question, I am telling you that, but we don't really need it. So it is rotating 44 rad and reaching to another angular velocity. The angular acceleration has a constant value of 1740 radian per second squared. Actually, the question is given the angular acceleration as 1740 radian per second squared. Find the final angular velocity of the blades. So we know omega 0, we know alpha, we know theta. We are looking for final angular acceleration. Remember in the equations, we had omega final is equal to omega 0 plus AT, no AT, alpha t. We know omega final squared is equal to omega 0 squared plus 2 alpha theta. System is accelerating, I'm interested in plus values. If it was decelerating, I would replace pluses by minuses, but here we are interested in plus values. Remember in these equations, let's say I'm in an exam, I'm looking at the list of equations in front of me, and I say, okay, let me see what I have in here and where I can apply this to get to what I want. I know alpha, I know theta, I know omega 0, so I need an equation that will be using these and give me the final omega. It would be this one, involving alpha, theta, initial omega, and final omega. So I'm going to be using this equation to solve for my final omega. Omega squared is equal to omega initial squared plus 2 alpha theta. And this is exactly what I'm looking for. Taking square root of each side, square will cancel in here, and omega, final omega will be equal to initial omega squared plus 2 alpha theta and square root. Then all we need to do is to enter all the values we know. Final omega, initial omega, 374 rad per second. This will be squared plus 2 times alpha, 1740, 2 times 1740 radian per second squared, times theta 44 rad. And this will give us an omega value, all in square root will give us an omega value of 541.21. So 541.29 rad per second is our answer. 542, 41.3, 541 would be also acceptable results in here, but I like always including 2 absolute decimals around in there. So this is the type of question we will have. Nothing really exactly new. We knew about angular velocity already. We knew about kinematics and linear kinematics already. We are only replacing alpha instead of A, theta instead of X, and omega instead of V, and doing the same calculations. One more problem I'm going to solve, and then I'll let you go. Let's look at another problem. And problems will be similar to this one we'll be solving. So it should be pretty straightforward, hopefully. Let's see what this problem says. A figure skater is spinning with an angular velocity of 15 radian per second. So let me try to draw a figure skater. A person skates on the ice. Let's put the hands like that, and a fancy skirt maybe, I don't know. So she, let's say this is a she, is skating, rotating. This is a very famous, this type of motions are very famous in figure skating. It has a velocity, angular velocity. This should be the initial velocity, 15 rad per sec. Okay, so a figure skater is spinning with an angular velocity of 15 rad per sec. She then comes to a stop. So as I am reading my question, I am thinking also. So comes to a stop. She then comes to a stop. What does that mean? Is that final omega will be 0 rad per second. She stopped. And what is she doing is decelerating. Right? I put this down as well. So I'm interested in equations with negative in front of alpha, right? In front of angular acceleration. During this time, her angular displacement is 5.1 rad. So during this time, her angular displacement is 5.1 rad. First A is asking what is her angular acceleration. Alpha. What is alpha? And second part is asking the time during which she comes to a stop. So second part is asking the time it takes for her to stop. T. Alright, let's think about this now. We have a deceleration. Every equation I'm going to use, I should put negative in front of terms involving acceleration, which is a rotational acceleration here, angular acceleration, alpha. Now, in the first part, I'm looking for the angular acceleration actually, right? And let's see what I know. I know initial omega 0, 15 rad per sec. Let's forget D in there. I know final omega 0 rad per sec. Slowing down, and I also know the angular displacement 5.1 rad. I actually am going to need the same equation we used before in the first question, because I know omega values, I know theta, I need alpha. So I have to use an equation involving alpha, theta, omega. Let me put the equation in here. Again, we have omega 0 plus alpha t. This is final angular velocity, this is initial angular velocity. Omega squared is equal to omega squared plus alpha t. And theta is equal to omega 0 t plus 1 over 2 alpha t squared. This is for acceleration. I'm going to replace negatives for deceleration. So I know alpha, I'm interested in alpha, omega 0, omega theta. I need an equation involving these. So this is 1. This should be 2 alpha theta, which would be this equation. But I'm going to replace negative in here because the object is decelerating. And there you go, I have my answer. The one equation I'm going to use to solve this is omega squared, final omega squared is equal to initial omega squared minus 2 alpha theta. Now I know this is 0. I'm going to take this to the other side. What I'm going to be left with is omega 0 squared is equal to 2 alpha theta. How I solve these questions generally, take negative to the other side as positive. I'll be finding this equation. 2 alpha theta is equal to omega 0 squared. Solving for alpha, we divide each side by 2 theta. Alpha will be equal to omega 0 squared divided by 2 times theta. Simple as that. Make sure you are comfortable with solving for anything in these equations. If you are not, come and talk to me in person. So alpha will be equal to initial omega 15 rad per second squared divided by 2 times theta 5.1 rad. And the answer should be, let me see what I have here. Please check my answer again. It will be a good practice for you. And do I have the answer? I actually don't have the answer. Oh, I do. 20.1. Okay. It should be equal to 22.1 rad per second squared. Please check this answer and let me know if it's correct. It should be correct. I did this some time ago, but yeah. So, we solve for alpha. We know initial final angular velocities. We know alpha. We are looking for time in the second part. Coming back to these equations, I need to find an equation involving omegas, initial final, and alpha and t, which would be this equation here. So I'm going to use that to solve for my time. Omega final is equal to omega 0 minus alpha t, because we are decelerating here, replacing plus with minus. And this omega is again 0. And I will end up with finding, taking this to the other side as positive, alpha t is equal to omega 0. Divide each side by t, each side by alpha actually, I'm looking for t, I'm going to leave t alone. Omega 0 divided by alpha will be my answer for time. Omega 0 is 15 rad per second. Divided by alpha, we found 22.1 rad per second squared. Our answer will be in seconds, and it should be 0.68 seconds. 0.7 second would be a good approximation to this, all acceptable. 0.68, again I put 2 decimals. So these are the type of questions we're looking at. Tomorrow we're going to solve a question in class, and then later on I'm going to give you pre-lecture quiz before Monday, but this time I'm not going to give you a pre-lecture quiz. See you tomorrow.